Hello students, let's continue the chapter gravitation as we have derived the expression for acceleration due to gravity at the depth d in our previous class, and we have already understood the concept of gravitational potential energy. So today we will derive the expression for gravitational potential energy, and we will understand the concept escape velocity, and we will derive the expression for escape velocity. Let's derive the expression for gravitational potential energy. For this, let us consider a body, that is particle of mass small m, in the gravitational field of another body of mass capital M. As you can see in the diagram, the particle which is having the mass m, that is small m, it is in the gravitational field of another body of mass capital M. So, to derive the expression for gravitational potential energy of a particle at a point P, as you can see the point P, what we have to do, the work done in moving the particle of a mass m from infinity to P is to be calculated. We have to calculate the work done in moving the particle of mass small m from infinity to that point P. Because what is gravitational potential energy? As we have already studied, the gravitational potential energy of a particle at any point in the gravitational field of a body is defined as the work done in bringing the particle from infinity to that point. So, we have to calculate that work done. Next, the work done of the particle. For this, the mass small m is displaced from A to B through a small displacement dx, as you can see in the diagram. For this, we will write the gravitational force of attraction between the body of mass m and the particle of mass small m separated by a distance x. What we can write it as, the gravitational force F is equal to capital G capital M small m divided by x square. We will consider this as equation 1. Next, the work done, we can take it as dw to move the mass small m, that is mass small m, through a small displacement dx. As I have already said, what we can write it as, the work done dw is equal to f dx. So dw is equal to, we will substitute the value of f, that is capital G capital M small m by x square dx. We will consider this as equation 2. Now the total work done in moving the mass small m from infinity to the point P is, we will integrate it, integration of dw is equal to integration of capital G capital M small m by x square dx. What are the limits of integration? That is infinity to r, because what is the point? Point will be the P and the distance is small r. And what is the, from where we are bringing? From infinity. So we will take the limits infinity to r. So next step, we will take the constant term this side, and what is the variable term? That is x square. So we will integrate that x square. So integration of dw is equal to constants. What are? G capital M small m integration, that is infinity to r, x raised to minus 2 dx. Okay, x raised to minus 2 dx. Next we will integrate that x raised to minus 2. So w is equal to the constant terms capital G capital M small m in the brackets of, what happens to the integration? X raised to minus 2 plus 1 whole divided by minus 2 plus 1 in So what are the limits? We will write it down. Infinity r. So W is equal to, solving it, what we get it as, write down the constant term as it is, capital G, capital M, small m in the brackets of, after solving we will get as minus 1 by x. So the limits are infinity to r. Next, we will take the minus sign here, that is W is equal to minus capital G, capital M, small m. So in the bracket of 1 by x, that is what are the limits? Infinity to r. Next, we have to substitute the limits, that is 1 by r minus 1 by infinity. Okay, what happens? W is equal to minus capital G, capital M, small m in the brackets of 1 by r minus 1 by infinity. So in the next term, 1 by infinity will be 0, because infinity, it is 0. We will consider that it as 0, because the particle, we have to bring it from infinity to that point. At that point, infinity point, the value will be 0. So W is equal to minus capital G, capital M, small m divided by r, because we have to take only 1 by r. So we'll consider this as equation 3. Now this work done W is stored in the particle as its gravitational potential energy U. So W is equal to U. What happens? U is equal to minus capital G, capital M, small m divided by R. We'll consider this as equation 4. So this equation 4 gives the expression for gravitational potential energy at a point due to a body of mass m. So this derivation is important as per your examination is concerned. Next, we will understand the escape velocity. The minimum velocity with which a body may be projected such that it is escaped from the gravitational pull of the earth is called as escape velocity. Okay, let's derive the expression for escape velocity. For this, let us consider a body at a certain height from the surface of the earth. As you can see in the diagram, that is the earth, and the body will be at a certain height from the surface of the earth. For this, let capital M be the mass of the earth and small m be the mass of the body, as you can see them in the diagram. Then the capital R be the radius of the earth, and small h is the height of the body above the earth's surface, and small r is equal to capital R plus h, which is equal to the distance of the body from the center of the earth, as you can see in the diagram. That is r plus h, capital R plus h is equal to small r. Next, VE. This is nothing but the escape velocity of the body. So G, small g is the acceleration due to gravity. Next, the gravitational force of the attraction between capital M and small m is separated by a distance, that is small r, as you can see in the diagram. The gravitational force of attraction between small m and capital M is separated by a distance r. We can write the gravitational force as F is equal to capital G, capital M divided by r square. That is, the distance is r, so r square. This is the law. Next, work done dw to move the mass m through a small displacement dr. We can write it as the work done dw is equal to f dr, and we'll substitute the value of f here. dw is equal to capital G, capital M, small m divided by r square dr. Let us consider this equation as 2. Next, the total work done in moving the mass, that is body of mass small m, from the surface of the earth to infinity, we will integrate it. Integration of dw is equal to integration of G, capital M, small m divided by r square dr. What are the limits of integration? R to infinity. Because the escape velocity is the minimum velocity in which a body may be projected such that it escapes from the gravitational pull of the earth. So, next step is we will take the constant term outside the integration, that is integration dw is equal to the constant terms are capital G, capital M, small m. So integration, the limits are r to infinity. What happens? 1 by r square, we will take it as r raised to minus 2 dr. In the next step, we will integrate that term. W is equal to capital G, capital M, small m. So what happens to integration after integration? R raised to minus 2 plus 1 divided by minus 2 plus 1. So the limits will be r to infinity. After solving it, what happens? W is equal to capital G, capital M, small m in the brackets of minus 1 by r. The limits will be r to infinity. So we'll take the minus term here, that is W is equal to minus capital G, capital M, small m in the brackets of 1 by r. The limits will be r to infinity. As we will substitute the values, what we get? W is equal to minus G, minus capital G, capital M, small m in the brackets of 1 by infinity minus 1 by r. Substituting the limits. Next, what happens? As you know that infinity will be 0. 1 by infinity will be 0. So what remains? W is equal to capital G, capital M, because minus minus it will be plus. So W is equal to capital G, capital M, small m divided by R. So we'll consider this as equation 3. This is the work done in converted into the kinetic energy of the body. This is nothing but the work done which is converted into the kinetic energy of the body. Next, what we'll do is kinetic energy is equal to work done. So what is kinetic energy? Half mv square. That v is nothing but the escape velocity of the body, that is ve. So half mve square, which is equal to capital G, capital M, small m by r. So the small m get cancels. So what left? ve square by 2 is equal to capital G, capital M by r. So only taking the escape velocity and taking 2 to the RHS. So ve square is equal to 2 capital G, capital M by capital R. So VE is equal to square root of, because VE square, so VE is equal to square root of 2 capital G, capital M by R. So this VE is the escape velocity, and this expression square root of 2 capital G, capital M by R is nothing but gives the expression for escape velocity. So in the next class, we will derive the expression for orbital velocity of the satellite and the expression for energy of the satellite. So today's two derivations are important as per your examination is concerned. Go through those derivations. Any doubt, ask me. Thank you.